everyone, in this video I want to provide an overview of SciPy and specifically see some demos of NumPy. So what is SciPy? Well, I have pulled up on my screen here scipy.org, which, as the website states, is a Python-based ecosystem of open source software for mathematics, science, and engineering. And then below this description, there's a list of the core packages, including NumPy, SciPy, Matplotlib, IPython, SymPy, and Pandas. In this video, I want to provide some demos of NumPy, which, as you can see here, provides a base n-dimensional array package. Many of these other packages are built on NumPy, so it's a great place to start when getting started with SciPy. All right, so I have VS Code open on my machine here with a empty main.py in a directory called NumPy_fun. So what I want to do here is introduce you to the NumPy array, or known more formally as the ndarray, where n stands for number of dimensions, or n-dimensional array. I'm going to do a lot of demos of NumPy arrays in this main.py. It would be great if you followed along just to get some practice typing out some of these functions and some of these operations, and then playing with them so you can see how the output changes. That will help you get more familiar working with this new type. All right, so let's start by importing NumPy. NumPy is typically imported as NP, and then anytime you're using a package level variable or function, you'll see something like np dot. For example, np.square root, in order to get the fast NumPy implementation of the square root function. All right, so let's start with a little review of lists. So let's say I make a list called X. I'll print it out here. Here's the output for a standard Python list. So I've created this from a range of numbers 0 inclusive to 10 exclusive, so I get the digits 0 through 9. I can make a NumPy array directly, or I can make one from a list. So since we're used to lists, let's see how we can make one using a list. So I'm going to overwrite X with np.array of X. So a NumPy version of X. Let's print it out, and let's also print out its type. All right, so it looks like we have the same contents in this NumPy array, except the output for printing X as an array versus a list is slightly different. We don't have commas separating our elements like we do with lists. We can get confirmation that X is now a NumPy array, not a list, by printing out its type on line 9, and we see that it is in fact a NumPy ND array. So oftentimes I'll just say array instead of ND array, but I'm referring to this specific NumPy type. Think about the ND array like a Python list, but on mathematics, engineering, steroids. All right. This was a 1D NumPy array. Let's do a 2D array. So let's say X is a list again, starting with what we know. So let's do a 2x3 list. So I have 2 nested lists. Each one has 3 elements. I'll print out X. This is a list just like we're used to. Notice that the output is all on one line. But if I make X a NumPy array, one thing that's nice about the output of a NumPy array is if it's multidimensional, then NumPy is going to give us a nice pretty print output where essentially our ND array is structured like a grid. So this is nice because we're used to reading data in things like spreadsheets where we have rows and we have columns. So here's the first element, here's the second element. They're on different lines, unlike our output from lists. Using X, let's explore a little bit more about the basics of working with NumPy arrays. For example, we can print out the dimension of our NumPy array using ndim, which is an attribute that belongs to x. Think about it like a variable that belongs to x. So this should give us 2 because we know there are 2 dimensions here, an x and a y, or a row and a column. We can figure out exactly what the shape is, number of rows by number of columns, by printing out x.shape. We get a tuple back with 2 elements. We know it's going to have 2 elements because the number of dimensions of this array is 2. So the first number is the number of rows, 2, 1, 2, and then the second is columns. And so you can see if we look down vertically here, 1, 4, 2, 5, 3, 6, those are our 3 columns. All right, let's also print out what the data type is of the elements in X. So if we print out x.dtype, okay, this is going to give us the data type of the elements in X. We see that there are int 64s, or 64-bit integers. I want to note that int 64 is different than the standard int type that comes with Python. Let's say we want to change this type. Perhaps we need more precision, and now we want to convert our integers into floating point numbers. We can do that with a method, which is a function that's associated with an object, like an array. And that method is called asType. So let's make a little note here. Let's convert x to be an array of floats. So let's do x floats is assigned x.asType, and then here's where we put in the type we want to convert it to. So let's do NumPy.float. So this says converts a string or number to a floating point number if possible. So we'll print it out again, see if it looks any different, and then we'll also print out dtype just to confirm that the type is in fact different. So here's our output from line 22. It does look slightly different. If you look at our previous output from line 15, we see that we have decimal numbers on each one, or decimal points, excuse me, on each one of our numbers here. So this is giving us a little visual indication that these are floating point numbers compared to integers. We can confirm this with line 23, where we print out xfloats.dtype and we see float 64, which is NumPy's float type. Okay, this is not the standard Python float type. All right, we've been creating our NumPy arrays from lists, but we can create them directly. For example, let's try creating this exact same list using a NumPy function, np.arange, in order to create the list. In order to create the array. So I'm going to pass in 10, and directly this is going to give us a NumPy array. No need to create a list and then convert it into a NumPy array. There's actually quite a few different ways to use arange, very similar to what you can do with the standard built-in range function in Python. For example, let's say I want to start at 2 instead of 0. Let's say I want to go up to 12 exclusive and go up by 2. So this will give me 2, 4, 6, 8, 10. So same as with Python's range, we can specify a start, a stop, and a step. Now let's take a look at some additional NumPy functions that could be used to create arrays directly. So let's say we need 10 ones. We can use the ones function to get 10 ones. We could also pass in a tuple for the dimensions if we need more than a 1D array of ones. For example, I could do like a 4, 5 to get 4 rows of 5 ones. I can do this same thing with np.zeros. And I can initialize an array directly full of zeros. One more function I'll show you now, and then in a few minutes we'll see another one in order to fill or initialize our arrays with random numbers. The one more I'll show you right now is full. So if you want to specify something other than 1 or 0, let's say we want 10 5.5s, we can use the full function in order to do this. There are 10 5.5s right there. All right, our next topic for introducing ourselves to NumPy arrays is indexing. For 1D arrays, indexing in NumPy works the same as with standard Python lists. So I won't do a demo of that because that's pretty straightforward. But it can be slightly different when working with n-dimensional arrays. So let's say I have, let's do the ones again. Let's say I have a 4x5 array of ones, and I want to print out the very, very first one. So that would be row 0, column 0. I can use double bracket notation just like I would use with lists. Since they're all ones, it's hard to confirm this is truly, in fact, the first one, but I can assure you that it is. Instead of using double array bracket notation, we can actually use single array bracket notation and then use a comma in order to separate our indices. So this is equivalent to this. Just another way to index multiple times into a multiple dimensional array. All right, this next topic of NumPy arrays is super, super important. And this is really why people use NumPy arrays over Python lists. And it's called vectorization. So essentially, vectorization is applying an operation to all of the elements in a list without having to write a loop to do it. Let's motivate this with an example. Let's suppose we have two equal length lists and we want to add their elements together. So let's solve this in Python using lists. So let's say I have a list of the first 10 numbers. Let's say I have another list of the next 10 numbers. So this would be starting at 10 and going up to 20. So they print out X, print out Y, so you can see what we're working with here. Okay, so I've got 0, 10, 1, 11, 2, 12, 3, 13, all the way up to 9, 19. So these are equal length lists. Okay, there are 10 elements in each. Let's say I want to produce a third list, Z, that stores the sum of these two lists. So index 0 in X plus index 0 in Y, so 0 plus 10 is 10. Index 1 in X plus index 1 in Y, 1 plus 11 is 12, so on and so forth. So to do this, we would create a third list, Z, and we would have a for loop where we walk through every index in X and Y, grab their elements and add them together, add the result to Z. So let's do it. So z.append X sub I plus Y sub I. Print out Z, and we should see the sum of the two. And it looks like we do. We'll just confirm, perhaps the last one, 19 plus 9 is 28. Awesome, looks good. But why do we have to write a loop to do that? Wouldn't it be nice if we could just do something like X plus Y and an element-wise addition would be performed? Well, this will actually compile and run in Python, but it's not going to give us the arithmetic addition between these two parallel arrays. Instead, it's going to concatenate the list together by essentially jamming Y onto the end of X. So here's X and here's Y jammed onto the end of it. So this doesn't give us that element-wise addition that we want. Now let's do the same thing, but this time using NumPy arrays, and we'll see that we can in fact write a one-liner like we've done on 53 and get the result that took us lines 49 through 51 to produce. All right, so I'm going to produce X and Y again. This time I'm going to use a range in order to keep practicing with it. So let's print out X, print out Y. They look good. Now let's make Z be X plus Y, and we'll print out Z. And there we have the same result as we have here. No loop was required. So that's one of the beauties of vectorization, is we can essentially use our operators with array operands and get element-wise application of that operand, or something of that operator on our operands. All right, there are a lot of operators in NumPy that are vectorized. You can imagine the standard arithmetic operators like addition, subtraction, multiplication, etc. Relational operators are also vectorized. So think about your less than or equal to, greater than or equal to, and not equal to. And this actually leads to some pretty cool applications of indexing with NumPy arrays. So let's do a kind of comprehensive example here that I assure you will be worth it because of how cool the output's going to be. All right, let's have an array of strings. I've been working mostly with numbers. Let's do an array of strings. So I'm going to make an array of strings that all start with M. So I call this M names. So we've got our Mary, our Michael, our Margaret, our Marcus, and our Molly. And just for fun, I'm going to put a duplicate Mary in here. So let's put another Mary after Margaret, but before Marcus. And then let's have a parallel array called M ages. So recall parallel arrays are equal length where data at corresponding indices match up. So for example, index 0 in M names Mary will correspond to index 0 in M ages, which will be this Mary's age. So let's say she's 28. I'm going to make these all line up nice so they're easy to see. Let's say Michael is 72. Let's say Margaret is 12. Let's say the other Mary is 34. Let's say Marcus is 40. And then let's say Molly is 68. All right, so we are going to get what's called a Boolean array by using vectorized equality. So let's just find out which one of the names are Mary by creating a Boolean array called Marys. We'll assign to it M names equal to Mary. Okay, so remember with vectorization, we can essentially use batch operations on data without writing any loops. So I can get an element-wise equality comparing Mary to each one of these elements. Okay, each one of these comparisons will yield true or false, and we will get a parallel array, Marys, storing those results, true or false. So here's our output. We get true, false, false, true, false, false. Okay, so if we look back up at our M names, we see trues in our output where there is Mary in the names, right? True, false, false, true, false, false. So now here's where this gets really, really, really cool. With a Boolean array, we can do what's called Boolean indexing. So let's say I only want to grab the Marys out of M ages, meaning I only want to get the ages for the Marys. What I can do is I can do Mary ages, and I can assign to that M ages sub Marys. What this is going to do is only index into M ages at the position where Marys is true, which would be index 0 and 3, which would give me 0 and 3. 28 and 34 which are in fact the ages for Mary. And there they are, 28 and 34. So pretty cool things can be done with relational operators and vectorization. Specifically, an example is Boolean indexing using Boolean arrays. I'll note a few things here, not with demos, but just verbally. So all the standard relational operators that I listed out earlier are vectorized. I will note that the Boolean operators that we have in Python, that would be the and, the or, and the not. These are vectorized, but not as and or not the keywords in Python. Instead, you'll use the ampersand for a vectorized logical and. You'll use the pipe for a vectorized logical or, and you have a few options for using not. So you can use tilde for Boolean arrays, or you can use np.logicalNot for integer arrays. So these are some fun things to try out. All right, let's move on to another topic which is related to vectorization. It'll be shorter, called broadcasting. So when you perform operations between differently sized arrays, that's called broadcasting. Whereas vectorization were operations between same-sized arrays. So let's see an example of broadcasting. So let's make n again, or excuse me, let's make x again. So let's say we want to multiply all elements in x by 2. So what I can do is I can broadcast the scalar 2 to every element in x. So you can see I've effectively doubled all of my numbers in x. What we've done here is multiply every element in an array by a scalar. We can also broadcast an array to an array, so long as, depending on what we're trying to do, the dimensions line up. Let me show you a brief example of this. Let's say I put 2 into an array. So it's effectively a singleton. I can broadcast 2 to x because one of their dimensions lines up. If I were to try this, say, with shape 2 for my broadcast to a shape 10, then this won't work. It says operands could not be broadcast together with shapes 10 and 2. All right, so let me undo that and get it running again. Let's move on to our next topic. I'm going to call this Advanced Assignment. In this section, we're going to see how we can essentially update multiple values in a NumPy array with a single assignment operator. All right, so to do this, we're going to work with random data. So let's do from numpy.random import randn. So randn is a function that could be used very similarly to zeros, ones, and full to create some data. So let's make some random data. We'll specify the dimensions of our data to randn. So let's do 3 rows by 4 columns. So here's some random numbers, random floating point numbers. We've got 3 rows and 4 columns. All right, if I wanted to do single item assignment, then what I could do is ran data, say sub 0 to grab the first row, sub 2, say to grab the third item, and overwrite that with, say, 100.0. Okay, like I said earlier, this works very similarly to Python lists. So here's our 100 right here. Note the scientific notation. All right. So here's the advanced assignment demo. So So let's create a Boolean array for all the negative values in our array. So we've got a few. So if I want a Boolean array representing all the negative values, then I would have true, false, 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 true, true, false, 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 true, true. Okay, this is going to be very similar to what we were doing with the Mary's demo, except we're going to be working with floating point numbers and we're working with an n-dimensional array, right? We've got a 3 by 4. All right, so let's build the array using vectorization. So negatives gets ran data less than 0. Okay, so here's our 3 by 4 Boolean array. Now let's say we want to set all the negative values to be 0. So here's the cool part. So ran data sub negatives, okay, so we're doing that Boolean indexing we saw earlier, but this time with a 2-dimensional array, is assigned 0. So this is batch assignment right here. We'll print out ran data and we'll see that where we had negative numbers are now all going to be 0. So for example, let's take a look at the first row. We have negative, positive, positive, negative. So we should have 0, 1.08, 100, 0. And that is in fact what we have. So that's also really neat because we didn't need a for loop in order to do this. All right, next topic here is slicing. So slicing an ND array works similar to lists. There are just a few subtle differences that I'd like to demonstrate for you. All right, so first, slices on lists return copies, but slices on ND arrays return views. So let's do an example here. So let's start with lists, because we're familiar with lists. Okay, so let's say I take a slice of x. Let's do, say, x sub 3 to 7. We'll print out the slice. Now let's say we modify a value in the slice. So let's do slice sub x sub 0 gets 100. Now I print out the slice and I'll print out x. And we'll see that the slice's first value is changed to 100, but we'll see that x's first value remains 0. Okay, so the key here is when we take a slice of a Python list, we get a copy. All right, let's say we do this exact same thing, but with NumPy arrays. So I'm going to be lazy here and just copy this. So let's do np.arange 10. Okay, so the exact same code, except x this time is a NumPy array. So on line 107, I take a slice, but this is a view, not a copy. So when I use slice x to update the first element, I'm actually updating the first element of a view that starts at index position 3 of x. So right here, looks like 100 has been updated in the slice, but it's also been updated in x, okay? Line 107 is what's called a view, okay? It is essentially a way to look at a region, work with a region of an array, but it is not a copy of the array. Okay, so keep this in mind. If you do in fact truly want a copy, then what you can do is call .copy on the view. Now, slice x is truly referring to a different NumPy array than x, and we see that this number here, 3, is not changed to a 100. And you can do this with Python lists as well. Lists have a copy method that you can invoke in order to get what's called a shallow copy. If you're interested in shallow copies, I highly recommend spending some time reading about shallow versus deep copies in Python. All right, let's do one more little demo here. Scalars can be broadcast to slices. So let's say we want a slice of x, say from 2 to 5, so index 2, 3, and 4, to be updated to 500. So 0, 1, 2, 3, 4. So we can use a slice in order to do batched assignment, like we saw up here in our advanced assignment demo. So another cool way to assign multiple values. All right, only a few more topics here. They'll be brief. Reshaping. So let's say we have a NumPy array that is, let's say, 10 by 10, but we want to reshape it into 25 by 4, etc. We can do that with the reshape method. All right, so let's get some data to work with. X is assigned np.arange 10. Okay, so we'll print out the shape of x. This is one-dimensional, so we get a tuple with a single value, which is 10, the number of elements in x. So let's say we want to reshape this into a 5 by 2. So we can do x is overwritten with x reshaped into a 5 by 2. We'll print out the shape again, and then for fun, let's print out x so that we can see it reshaped. Awesome. So far, so good. Let's do transposing. Let's continue working with x. So x right now is a 5 by 2, but let's say we want to transpose x into a 2 by 5. A little bit of matrix-like operations here. We can do x dot t, and this will give us the same values of x, but transposed into a 2 by 5. All right, our last topic here is talking more about ndarray functions. Okay, so ndarray has several fast vectorized universal functions. Universal functions are often shortened into ufuncs, and ufuncs perform element-wise operations on data. So very similar to what we were seeing with vectorization via operators, we're going to see with functions. I've got pulled up here in Chrome the NumPy documentation on ufuncs that I encourage you to read through. But here, in kind of a longer description, NumPy says that a ufunc is a function that operates on ndarrays in an element-by-element fashion, supporting array broadcasting, typecasting, and several other standard features. That is, a ufunc is a vectorized wrapper for a function that takes a fixed number of specific inputs and produces a fixed number of specific outputs. So let's see an example of some of these ufuncs in action. So let's start with unary ufuncs. So unary ufuncs operate on one operand. For example, let's say we have x np.arange 10. We can compute the square root of every single element in x with np.square-root. This is an example of a unary ufunc because it takes a single argument. It operates on one operand, which is x, the array. So you've probably seen square root before, for example, from the math module. So Python's math module square root is not vectorized. Okay, it operates on a single scalar element. What we have here is essentially a call to np.square-root that applies a square root to every single element in x. which is pretty cool. Once again, with these ufuncs like vectorization and broadcasting, we don't need to write our own loop to get our output. So for a full list of available ufuncs, take a look at the NumPy documentation. There are tens of them, like over 60 or more. Most common operations that you would need in math are going to be implemented in NumPy as really fast ufuncs. All right, as you can imagine, if we can have unary ufuncs, we can also have binary ufuncs. So binary ufuncs accept 2 operands, right? Typically, we're talking about parallel arrays here, like, for example, addition we saw earlier with the operator. So let's grab another array here. Let's do a range, say, let's do the ones we were doing earlier, 10 to 20. So let's do print np dot add, and we can add x and y together. So here's that same output that we were getting earlier, but instead of using the addition operator, instead we're using the underlying binary ufunc that essentially is implemented and called whenever we need that vectorized addition via the operator. All right, let's do a few more demos here just for fun, because we already saw addition earlier. Let's do np.power. So let's say we're going to pass in x, and then we need to have a second array that's going to list out all of the powers that we want to raise each element of x to. So we could use y, but those are pretty large numbers that I have in y. So why don't we make a new array? So let's say we want to raise every value in x to a power of 2. So we need 10 numbers, and those numbers need to all be 2s. So if I do this, I have 0 through 9 squared, right? 8 squared is 64, 9 squared is 81. What's nice also about using np.power as a demo of a binary ufunc is we can pass in a scalar for our value to raise every element in x2. I don't have to pass in an equal-sized array. Instead, I can pass in a non-array, a scalar, and it'll be broadcast to every element of x. So let's see that in action. Let's just raise every single element to 2.0. No need to make an array like we did before if they're all going to be the same. And there we get the same output. All right, so that's probably good for now, introducing NumPy ufuncs and NumPy and its ndarray type in general. I'll refer you back to the NumPy documentation to read more. I'll also point out that if you go to the ufuncs page in NumPy, you can search for available ufuncs, and you'll see that there are currently more than 60 universal functions defined in NumPy, and they cover a wide variety of operations. For example, here's the math operations. So we saw add, for example. We also saw power, but look how many more there are here. Here are trig functions, bit twiddling functions, comparison functions, all sorts of really great functions. And a lot of these are essentially executed when you use the corresponding operator. For example, greater than. This is the NumPy function that's executed when you use a greater than operator with NumPy operands, NumPy array operands. All right, hopefully you learned a lot about NumPy and you have some ideas for how you can start to use it in your mathematical, science, or engineering-based coding projects. Thanks for watching.